Hello. In the previous video, we have proved that the Joule Thomson coefficient for an ideal gas is equal to 0, or an ideal gas do not show any heating or cooling effect on undergoing a throttling process. Here we will discuss the Joule Thomson coefficient for real gases, which are described by the van der Waals equation. They are also known as the van der Waals gases. So as we have done in the case of the ideal gas, let me begin with the definition of Joule Thomson coefficient. That will be helping us because that will give us a direction for our derivation. The Joule Thomson coefficient, I am writing in short JT coefficient, is given by mu equal to dou T by dou P at constant enthalpy H, equal to, we had different forms, I am writing only one form, 1 by Cp into T dou V by dou P, sorry, dou V by dou T, right, dou V by dou T, pardon me, at constant pressure minus V. So let me say this is our leading equation. So let me call this one as equation number 1. Okay. So what we are going to do is that by introducing the van der Waals equation for real gases, we'll derive an expression for this dou V by dou T, and then we will substitute in this equation and we will see what is the fate of this equation, right? So let's start from the van der Waals equation for 1 mole of a gas. Okay, so we have the van der Waals, let me write van der Waals equation for 1 mole. What is that? That is, it becomes P plus A by V square into V minus NB will become V minus B. V minus B equal to RT. Right? So let me say this is my second equation, which I can modify. Let me open the bracket on the LHS. So this equation can be again written otherwise. So on opening, what will be the thing? It becomes PV. So first term P into V, PV, then minus PB, okay. So then these terms, so it will be AV by V square, so it will become what? 1V will get cancelled, so it becomes plus A by V, right, minus the last term, okay, minus AB by V square, minus AB by V square, and on the RHS it is same as RT, right? So that is on simplification or opening the bracket, which can be further simplified. You know, this A and B, which are the van der Waals constants for the particular gas in question, they are actually very, very small. A and B are pretty small, you know. So since A and B are very small compared to V square, where V is the volume of the sample, we can neglect this particular term. AB by V square term can be neglected compared to the magnitude of other terms, right? Because the numerator is very small compared to the denominator, so automatically that quantity can be neglected. So there is a sort of approximation that we do for the ease of our derivation, okay, and that's of course justified. It will be within the permitted errors of our derivation. So what will be this equation becoming? So this equation becomes PV minus PB plus A by V is it not? Up to there only is there, plus A by V is equal to RT. So let me call this equation as equation number 3, right? So it's valid approximation. Now let's modify it further. So from that, let me write what is PV equal to. Remember, our motivation is that we have to finally take dou V by dou T, and trying to separate out all the terms whatever is needed. So let me write from that, therefore PV equal to what will be that one? You take the other quantities, so that is RT is already there on the RHS, RT plus PB, RT plus PB, minus PB becomes plus PB, so minus A by V, is it not? Minus A by V, right? Which can be again, okay, because I don't need a V there, so let me see, just I can rewrite. So it is equal to further RT plus PB. So PB is a constant term, so when I do the derivative, that will reduce to 0. That is my advantage, okay, or I'm not going to change it. So minus, so V, see, V can be substituted, okay. So there's a little bit of approximation that we are doing here. So V can be written as RT by P, okay. So I'm writing V is equal to RT by P, but that will just a moment. How we can write that V? 1 minute. Yes, just a moment. Yeah, let me do by another method. There is some sort of an issue here because I thought of the other one. Yeah, we can go by the other method. So I thought I have seen another derivation, but I don't find that derivation justified because they are substituting. Okay, you think on this one. Yes, they are substituting for V in terms of P, R and T, okay, but that can be done only for an ideal gas. So let me do one thing, let me go back here, right? So sorry for the this confusion. So just let me again go to equation number 3. So that is there, equation number 3 is there, that is PV minus PB, and let me cut off this one, sorry for the trouble. Yeah, so what we can do, we can directly differentiate. Equation number 3 with respect to T, keeping P as a constant. So what do we want differentiating? So differentiating, we write here. So differentiating 3 with respect to T, keeping P equal to constant. Keeping P equal to a constant. So what will be that one? It will give you P into dou V by dou T, at P minus, right? So the second term, as I told you, this PB term on differentiating, that will be vanishing, that's equal to 0. So what we are left with is this A. So it is 1 by V, right? 1 by V. So that will be minus 1 by V square into dou V by dou T, right? Okay. So it will be minus A by, I can say A by V square. So plus becomes minus, that's why there is a minus sign there. Minus A by V square into, okay, function of function rule. So dou V by dou T, right? That's equal to, on the other side, when you do it, it will be leaving R only, T is gone. Okay, so that is there. Now I can rearrange it. You can see this, yeah, of course, P is constant here also. Dou V by dou T at P, that's a common factor out of these two. So what I can do is that I can take that one as common. So dou V by dou T at P, and that's the quantity that we need as per equation number 1. So at P, that is taken as common factor. So into P minus A by V square, right? Minus A by V square, that's equal to R, right? Now further, it will give you dou V by dou T at P, okay, right? At P, that's equal to R divided by P minus, just rearrangements, A by V square, A by V square. So let me give some number for this one. Let me call this one as equation number 4 for the time being. Okay. Now what we can do, we can from the equation number 2, which is the van der Waals equation for 1 mole of the gas, we can write P equal to, from equation number 2, we can write P is equal to, on rearranging, you take V minus B to the bottom, so that is RT by V minus B, RT by V minus B, minus A by V square, right? Minus A by V square, right? So let me say, actually this is nothing but, yeah, it's called as equation number 5. So now let's use equation number 5 in equation number 4, okay? So therefore equation number 4 is modified as dou V, it's a bit lengthy, that's all, dou V by dou T, it's a little bit of approximations, of course we are doing, at to P, dou V by dou T at P, that's equal to R divided by, right? So what is there? R by P minus A by V square, right? P minus A by V square. So instead of P, I will substitute, so I am using a square bracket. For P, I am substitute from equation number 5, that is RT by V minus B, RT by V minus B, minus A by V square, right? Minus, then there is, so I have substituted for this P, there is already a minus A by V square there. So minus A by V square, right? So that is the dou V by dou T at P, right? Which can be further simplified. It's equal to, I'm doing 2 steps now. See what I'm doing. So this minus A by V square minus A by V square can be combined. So it becomes minus 2A by V square. Then what I'm doing, there is a V minus B here, okay, in the denominator of the first term. So what I'm doing, I'm just multiplying the numerator and denominator by V minus B, okay? So that's what I'm going to do. So what will be this equation becoming? This equation becomes R into, just check it, V minus B. So I'm multiplying V minus B in the numerator. So I have to compensate it by multiplying V minus B in the denominator. Okay, right. So what will happen, as far as the first term is concerned, there is already a V minus B in the denominator, so that V minus B will be getting cancelled. So that is RT minus, the other term was 2A by V square. So it will become 2A into that extra term, that is V minus B, by V square, by V square. Okay, hope that is okay with you. So now, let me do one more thing. So there is V minus B. There is V minus B term here, right? V minus B term is here. And in the denominator, what do you have? You have got a V square term here. Okay. So compared to the V square term, okay, this V minus B term can be written as what? Simply B, simply V. Okay, because B is very, very small compared to V, right? So what I'm doing only in the denominator, see that there is the same term V minus B is there in the numerator or in the denominator, but I'm doing this change only in the denominator, because that will not make significant changes in our values of the quantity. So what I'm doing is that in the denominator I'm writing v minus b as simply v. Okay, b is neglected. The reason is that because there is v square in the denominator, so compared to this one, this quantity can be very, very small. That is the reason, right? So what will be this equation becoming? Therefore neglecting, I can say if needed, okay, or you can directly do that. These are all within the permitted errors of any derivation. Neglecting b in the denominator, okay, compared to v minus b. What will be this one? So I will get dou v by dou t at constant pressure, that is equal to, I'm not doing anything with the numerator there, I'm retaining v minus b divided by RT minus, so what is the advantage of that approximation? You know, this v and this one of v will be getting cancelled, so what is left out there is 2a by v only, 2a by v. So I may use a bracket, right? So we say this is, let me call this one as some equation number 6, right? A bit lengthy, but okay, there is no much complexities. We go to the next page, next slide. Yeah, so we obtain dou v by dou t to p. Let me multiply with the t on both sides, right? So therefore t into dou v by dou t at p, just we multiply, that's all. That will be equal to, on the other side, so there was r into v minus b, it will become rt into v minus b, right? Rt into v minus b divided by, what was there? There was rt minus 2a by v in the denominator, right? Now I can modify this one once again. So if I just modify this one, so it will be v minus b. Suppose I am taking this rt term to the denominator, or I am dividing by rt throughout, okay, in the numerator and denominator. So it will be simply v minus b, just rearrangement, divided by, so rt is gone, so that the denominator will be 1 minus 2a by rtv, right? Hope you understood it. Simple. Which can be further written as v minus b into, see this term I can take to the, this entire denominator can be taken to the numerator, so it will become raised to minus 1, right? So it becomes into, many of these steps can be skipped, but I am just doing it, minus 2a by rtv whole raised to minus 1. Now you look at this particular quantity, 2a by rtv. You know, this a is the van der Waals constant, and compared to v itself, this van der Waals constant is very, very small, or both a and v are very, very small compared to the other quantities involved. So I can say that this, of course, this 2a by rtv is going to be anywhere less than 1, right? The 2a is very small compared to rtv, right? So this is of the form 1 minus x, right, raised to n. And what we can do, we can go for the binomial expansion, right, whenever this x is very small, less than 1. So I can go for the binomial expansion, and since this quantity is less, what I can do, I can truncate all the higher terms and I can retain only the first term, right, only the first term. So it will be 1 minus nx, so it will become plus. So this equation becomes, it's equal to neglecting all the higher powers of 2a by rtv, we can write this is equal to simply v minus b into 1 minus will become, this minus 1 should be multiplied here, so it will become 1 plus 2a by rtv, 1 plus 2a by rtv, right? which if you open the bracket, that's equal to v, okay, minus b plus 2a into v minus b by RTV, okay. Now we make further simplification here. So here you can see there is v minus b here, then plus 2a v minus b by RTV. Once again you have got a chance to neglect this b, not here but here, because this term is not going to get affected much even if you neglect this b here, because there is v there in the denominator also, okay. So which can be written, remember we are just doing a number of approximation which will not affect our final equation much. So it will become simply equal to v minus b, the first term I am retaining as such, plus what will happen if you neglect b here, this v and this v will be getting cancelled. So what is left out is only 2a by RT, okay. So we call this one by some name, some number. You see what was the number? Yeah, we use up to 6 and we use equation number 7. Say this equation number 7. So how do you get it? Neglecting b in the numerator, okay, right. It should be understood. We don't do that one here because that is a direct subtraction and the other one is a fraction. Okay, in the fraction the contribution of this term b is very, very small. That is why we are neglecting only in the fraction. We are not neglecting the b here, which is directly added or subtracted. Okay, right. So that is the thing. So what was the LHS? That is t into dou v by dou t to p, right? Now we are okay. We have obtained the quantity to be substituted. Therefore, let me just, what is our equation number 1 becoming? What was our equation number 1? Where we define mu. Okay, 1 gives you mu. Mu is equal to 1 by Cp, right? 1 by Cp. That is the definition for mu. That's all. Into the equation was you can just look back. See, 1 by Cp into t dou v by dou t at p minus v. So we have just found out an expression for this one. So I have to substitute there. So that's substituted. What is that? That is v minus b plus 2a by rt, right? Then there was a minus v there, so this minus v and this minus v will be getting, sorry, plus v will be getting cancelled, right? So it gives you, what is that? Mu equal to 1 by Cp. It's reduced now. So this is I can rearrange this one as simply 2a by rt minus b, 2a by rt minus b, right? Or, so that is our final equation. If you want, you can just take this one as a final equation. That's equation number 8. Or since mu is equal to, what does mu equal to? Dou t upon dou p at constant h. I can rewrite this expression as dt equal to, instead of, because already we have maintained h as a constant in the derivation. So finally I can write dt, right? dt is equal to, what is that? Mu times, and what is mu? Mu into dp, and I can substitute for mu from this expression 8. So that is equal to 1 by Cp times 2a by rt minus b times dp. So that will be my equation number 9. Here we are. Okay. So you can either depend on equation number 8 or 9 to make some meaningful conclusions. So let me just see, either this expression will do for mu, or for dt I can use this expression. Both these equations are equivalent, right? Now I think we can discuss the different cases, right? See, if case 1, right? Case 1, if you can see whether cooling effect or heating effect will occur. That will depend upon the value of mu, right? Or the value. So you know the value of mu is decided by, the sign of mu is decided by this quantity in the bracket, right? So I can say the same quantity is appearing here also, right? So whether dt will be positive or negative will depend upon this quantity, right? So I am taking that one. So if 2a by RT, if 2a by RT, right, minus b, I can take it like this, minus b, that entire bracket, if that is greater than 0, okay, let me take it like this, or I am interested in the temperature, or can you rearrange the temperature, this equation in terms of the temperature, or the temperature T is less than, on rearranging that one, T is less than 2a by, so B will be going to the place of temperature there, RB, right, 2a by RB. If T is less than 2a by RB, then what will happen? See, this term is taken to be positive, and you know in throttling process dP is supposed to be always negative because of the reason we have discussed, because in throttling process the gas is moving from high pressure to low pressure, okay? So PF is always less than PI in the case of throttling process. So therefore dP, which is equal to PF minus PI, is what? Always negative for throttling process, right? So since dP is negative, dt will be negative if this quantity is what? Positive. So I can say that dt, then dt is negative, and we have concluded what is the meaning of dt negative. It means that there is a cooling effect. Cooling occurs. That's the condition. So just note this particular value of temperature, right? Now, second case. I think I can go to the next page. Case 2. Sorry. Yeah. Case 2. If 2a by RT minus b, if that quantity in the bracket is equal to 0, or rearranging, T is equal to simply 2a by, T is equal to 2a by RB, then what will happen? You know, dt is equal to 0. dt 0, you know what's the meaning? In that case, there is no heating, no cooling or heating. So we can say that at this particular temperature for a real gas, there won't be any Joule Thomson effect. It means that a real gas will be behaving like the behavior of an ideal gas. We have seen that an ideal gas will never show Joule Thomson effect, right? But here you can see that the real gases or van der Waals gases will also show a behavior similar to that of an ideal gas at a particular temperature, and we will call this particular temperature, okay? So at this particular temperature, we will see that the Joule Thomson coefficient mu will be equal to 0. So at this temperature, okay, mu will be equal to 0, and we will call this particular temperature as the temperature of inversion. Temperature of inversion for a gas. Inversion. Okay, temperature of inversion. So that is something very, very important. I'll come back to this temperature of inversion at the end. Okay, now the third case, let me discuss the third case, case 3. So what is that case 3? The quantity in the bracket, that is if 2a by RT minus b, if that is less than 0, or in other way in terms of the temperature of the sample, if T of the temperature of the sample is greater than 2A by RB, right, then what is that? dt is positive. dt is positive, right, because dp is negative, so dt will be finally equal to positive, or what will be there? There will be a heating effect. So this is okay, something really interesting. Means a real gas or a van der Waals gas can undergo either heating or cooling, or there won't be any change in temperature at all once it is made to undergo the throttling effect. So it all depends on, we can see that it depends on the initial temperature at which the gas is made to undergo throttling. Okay, see what's the meaning? We have seen that in the throttling phenomenon, yeah, right. So you have got a porous plug somewhere here, right, a porous partition is there, and a gas is initially at a PI, some high pressure, and there is a PF, low pressure, and the gas is made to, right, a gas is made to undergo an expansion from a low pressure, a high pressure region to low pressure region through a valve or a throttle, right. So there is some temperature. The gas sample is taken into the compartment at some particular temperature T, and this temperature is the temperature that appears here, that I am calling as the initial temperature. Initial temperature, okay, and the initial temperature can be the room temperature. Suppose you are taking hydrogen gas or you are taking oxygen at room temperature into the compartment of the Joule Thomson apparatus, and you make that oxygen sample to undergo Joule Thomson expansion at room temperature. Okay, so if the room temperature for oxygen, okay, you know, for every gaseous sample there is some characteristic value for A and B. Van der Waals gases, van der Waals constants are different for different gases. For each sample of the gas, there will be some particular value for A and B. Okay, for oxygen there will be a set of value for A and B. For hydrogen there is set of value for A and B. So depending on the A and B values for that particular gaseous sample, okay, there will be a particular value for this particular temperature, what I have boxed here, which I named as what the temperature of inversion. Okay, so if the initial temperature, that is the meaning, if the initial temperature means the temperature at which the gaseous sample is made to undergo throttling phenomenon. If the initial temperature of the real gas, any gas, if that is less than the temperature of inversion, remember this temperature I am calling temperature of inversion, denoted by Ti. Okay, then if the initial temperature of the real gas is less than the temperature of inversion, right, so you can see that from the previous conclusion. Okay, see, if T is not K, yeah, less than the what do you call the temperature of inversion, then you will see that the gas will undergo cooling. The gas will undergo cooling. That is, if I can say like this, if T less than, T means initial temperature. See that this one I have named as Ti. Okay, if T is less than Ti for the particular gas, for every gas there is a definite value of temperature of inversion. From gas to gas, the temperature of inversion is different. Why? Because for each gas there is a separate value for A and B, even though R is constant. So I can find out the temperature of inversion for each gas, right? For some gases it's greater than the room temperature. For some gases it's but lesser than the room temperature. Okay, so hope you remember when we mentioned our introductory lecture, we have seen that, we have said that, okay, the hydrogen was an exception. Okay, hydrogen and helium are exception, right? So instead of at room temperature it will undergo heating effect instead of undergoing cooling effect. The reason, because it is related to the temperature of inversion of hydrogen and helium, right? So if T is less than Ti, the temperature of inversion, then cooling will occur, and if the initial temperature of the gaseous sample is greater than the temperature of inversion for that particular sample, then heating will occur, right? That is the relevance of this quantity, what is known as temperature of inversion. So how do you define the temperature of inversion? The temperature of inversion can be defined for any gas as the temperature at which, or temperature of the gas at which the Joule Thomson coefficient becomes 0, right? Is not the meaning? Because we have obtained this Ti by substituting 2A by RT minus B equal to 0, and you know that's this, when 2A by RT minus B equal to 0, automatically this expression mu, right, this mu will be equal to what? 0. Mu equal to 0 when, this one, mu equal to 0 when this 2A by RT minus B equal to 0, this equal to 0. Okay, from that only you obtain this expression for T. That's why we say that the temperature of inversion of a gas is the temperature at which the Joule Thomson coefficient becomes 0, right? And if the initial temperature of the gas is less than the temperature of inversion for that particular gas, then cooling will be happening after throttling. And if the temperature of the gas is greater than the initial of the temperature of inversion, then heating will occur. And that is the relevance of temperature of inversion. So we conclude the session by recalling that ideal gases do not show Joule Thomson effect because its Joule Thomson coefficient is always equal to 0. But real gases, or otherwise known as van der Waals gases, can show Joule Thomson effect depending on its initial temperature. If the initial temperature of a given gas is less than its temperature of inversion, then cooling will occur, and if the initial temperature of a real gas is greater than its temperature of inversion, heating will occur, where temperature of inversion is the temperature at which the Joule Thomson coefficient mu is equal to 0 for that particular van der Waals gas, and that's given by 2A by RB, where A and B are the van der Waals constant for that particular gas. So with this session, we conclude our module number 4, which was rather a lengthy one, and see that you go through the syllabus and check whether we have left out any important topic. And I think that we have tried to do justice to the particular syllabus, and if anything is left out, you can bring it to my notice. Okay, so we conclude here. Thank you.